Okay, it's 12 o'clock, so welcome for the first installment in this year of Polish NMR Seminar Series. Today we'll have, as usual, two talks. The first student talk will be by Gabriela Szczupaj from Center of New Technologies, University of Warsaw. And the main talk will be by Dr. Piotr Klukowski from Institute of Molecular Physical Science, ETH Zurich, in Switzerland. Sorry, I got some strange, okay. In Switzerland. And as usual, a short announcement about the best student question competition. So as most of you probably know already, we have this semester the competition for the best student question. If you want to win some set of PT Polish Chemical Society gadgets, ask some interesting questions to our speakers. Remember to introduce yourself so we'll know who you are, or at least have your full name in Zoom. And going back to today's topic, we'll start with Gabriela. Her topic will be inclusion of complexes of quinidine with cyclodextrins. And the floor is yours, Gabriela. So you can start sharing your screen.
Thank you. First, can you hear me?
Yes, we can hear you.
Okay, perfect. Okay.
We can see the screen. Good.
Okay, perfect. So as Mateusz already said, my name is Gabriela Szczupaj, and I'm doing my PhD in Krzysztof Kazimierczuk's lab under the assistant supervision of Michał Nowakowski. And today I'm gonna tell you something about the part of my PhD project, which is inclusion complexes of quinidine with cyclodextrins. So the main star of my project is, as already mentioned, quinidine, which is an alkaloid obtained from the cinchona tree bark, and is used, for example, as a drug for arrhythmic treatment. And it's not always the best option, so we are trying to find out how to improve the usage of quinidine. And one of the ideas is to use it with cyclodextrins as an inclusion complex. So the cyclodextrins, the other stars of my project. I use naturally occurring cyclodextrins, which are alpha, beta, and gamma. The only difference between those three is the cavity size, like in general, the size of them, because they are composed of 6, 7, or 8 glucose parts. And it leads us to my first scientific question for my project, which is how does cavity size affect the formation of inclusion complexes? The other things I study are the influences of environment. Is the influence of environment on the inclusion complex formation. The first one is the temperature, and the other one is the pH. So the second question in my project is how the environment affects the formation of inclusion complexes. And the pH, specifically, we study because of the two protonation sites in the quinidine, which are here on the nitrogen and here on the nitrogen. And the last scientific question in my project is, are the results of theoretical modeling of inclusion complexes consistent with experimental results? So how it works. My project roadmap starts with performing a complete assignment of chemical shifts to the atoms of alkaloids studied in water and determining the effect of pH on chemical shifts. And this part is already done. I have the TOXI and HSQC spectra performed and assigned. So I have the full assignment of the quinidine atoms. And also I performed the 1D spectra of quinidine with in different pH. As you can see on the shown picture, the signals shift with the change of pH. At the bottom we have the low pH, and at the top we have the high pH. So as you can see, the chemical shifts are changing. So we have to choose some of those to perform the measurements for the temperature, and with cyclodextrins to make sure that the pH is not influencing the shifts. And what we observe is the change because of the temperature or the concentration of the host. So I chose the 2.5 pH, 7.4, and 10.75. And the next step is to perform the NMR titration for each of the complexes of quinidine with the natural cyclodextrins, and determining the binding constant depending on the temperature and stoichiometry of the resulting complexes in different pH. And for that, I'm gonna show you how the host concentration influence the chemical shifts of the quinidine. So at the bottom, again, we have the low concentration, like the first one is without the cyclodextrin spectrum, and the higher ones are with the higher concentration of the host, which is the cyclodextrin. As you can see, not all of the signals move, but some of them, for example, this one is the aromatical part shown. For example, this one moves a lot, and that's what we expect and what we actually use for the calculations. And the other thing I wanted to show you is the temperature influence on the complex formation, and you can see the chemical shifts are moving, and for all of the signals. So based on those, I calculate the association constant and the stoichiometry of the complexes. For example, for the quinidine with alpha cyclodextrin in pH 7.4, I obtained the best results for the stoichiometry 1:1, and all of the results are shown here in the table. Here you have the association constant, and I know it's not really easy to analyze it in a table, so I prepared also the plot where you can see that there is a linear change with the temperature of the association constants, which already leads us to some of the conclusions in which temperature, for example, is better to prepare such a complex, right? Yep. So that was the second step of my project, and the last part is to perform docking between quinidine and natural cyclodextrins and comparing the results obtained with experimental data. This part I still not have done yet, so it's yet to do. Hopefully I'm gonna show you on another seminar the full results. Yeah, so it's gonna be all from me, and thank you very much for your attention.
Thank you very much, Gabriela, and we are open for the discussion. If you want to ask questions, please turn on your microphone, if possible, camera, and start asking. Do we have any questions? If not, maybe my warm-up question. So your lab is well known for the lab of radon transform. And looking at the spectra where you have a series of spectra with moving peaks, I just have to ask, why you haven't used radon there?
Well, To be honest, actually, I know I'm in the Krzysztof Kazimierczuk's lab, but my focus is mostly on the usage of the NMR to study biomolecules. So usually I'm like most focused on the like what informations I can get from the spectra and not how to like make it beautiful and like perfect.
Should I add something?
Yes, of course.
Yeah,
If you
so
want.
simply radon transform is a good method of boosting sensitivity. If sensitivity is not a problem, then actually acquire a conventional series of spectra with the standard linear fit is more effective. And we even had paper about this in JMR several years ago with Agustin Romero and Paweł Kasprzak where we compared the two methods, the conventional analysis like Gabriela is doing and radon transform. And radon transform is better if sensitivity is a problem. But you get more precise results if you use linear fit when signal to noise ratio is sufficient. So that's the main argument. Second thing is that for pH dependence, you have the sigmoidal plots, and you would have to create a special variant of pseudo radon transform with nonlinear dependencies, which we haven't done, but that's interesting. We will probably reuse this data for our project. We'll see. But there is no need to do it. I mean, the conventional analysis is proven to be better, even theoretical.
Okay,
Thank you very much,
Krzysztof.
Krzysztof.
Okay, do we have any other questions?
Maybe I have a short one.
Sure.
Can you hear me? Yeah.
Yes.
Okay. So do you have any evidence that the quinidine enters inside the cyclodextrin?
Yeah, I mean, the moving signals is the evidence basically. Like, let me go back to no, too far. Here, like, we can see that not the whole quinidine enters the cyclodextrin, just some part of it. And we can observe that based on the switch of the chemical shifts of signals.
Yeah, but these are chemical shifts, changes of chemical shifts of quinidine. So, but how it really interacts with cyclodextrin? Is it like from outside or from inside?
From inside.
So do you have like how do you know that it's from inside?
Well, first of all, it was already studied for quinine, which is like completely similar to quinidine. It's yeah. So here, the only difference between quinine and quinidine is the orientation of OH group here. So for quinine, they already shown that it enters inside, and sometimes it's like this part, and sometimes it's this part that enters the cyclodextrin and influence, and is like creating the inclusion complex. So, I mean, at least like starting from this, I would assume that it's the same thing happens for the quinidine.
Okay, and this nucleus whose chemical shifts moves most, which one is it?
Which atom, right?
Yeah, which atom? Yeah.
So that one, I try to remember right now because I don't have it like on the
Okay.
on the plot. I have to check it. Like I don't remember for which one was like the most switch, because it's not like only one. There are like few also on the aliphatic.
Thanks.
Thank you.
Okay, we have one question on chat from Svetlana Simova. Do you see CS changes in CYD?
And do I see changes in what? I'm sorry.
Do you see CS changes in CYD? Svetlana, maybe you could turn on your microphone and ask in person. It's possible.
Yes, the question is chemical shifts. Does she observe the chemical shifts of the changes of the chemical shifts in the cyclodextrin molecules?
Oh, okay. Yeah. It's hard to see the changes in the chemical shift of cyclodextrin because the difference of the concentration is, I mean, we have a small concentration of quinidine because in general it's not the molecule that likes to dissolve in water. So I kind of struggle with the concentration, so it's very low. So the changes in the chemical shift of cyclodextrin coming from the inclusion complex formation are so small that we can't observe them. Like
Okay, then to my opinion, you have to do Roisy spectra to be sure what actually is inside. Because if you have changes in the cyclodextrins, then you can say these are the inner protons, H3 and H5, or these are the other protons. So then the best will be to make at the different conditions Roisy spectra of the complexes.
Yes. Actually, we have it in our plan to perform the Rosie spectra for like chosen concentrations of the cyclodextrin with quinidine. Thank you very much for your insight.
Gabriela,
Okay.
but can you hear me?
Yes.
We can.
You mentioned the low solubility. Do you have enough sensitivity for Rose spectrum?
We will see. I would
Okay.
try. I mean, it doesn't hurt to try.
Definitely not. Good luck.
Okay,
Thank
I
you so
think I
much.
have to cut the discussion due to the time constraints. So thanks all for asking, keeping this discussion alive. And now we go for our next talk. So let's invite. Just a moment. Something. Okay. Okay. Now, so let's invite Dr. Piotr Klukowski from ETH Zurich. He will give a talk titled Deep Learning and High-Field NMR, Recent Advances and Future Perspective. Sorry. Piotr, the screen is yours.
Perfect. Can you see my presentation now?
Yes, we can.
So thank you for the introduction and for the invitation to Polish NMR seminars. And as it has been mentioned, the title of my talk is Deep Learning and High-Field NMR, Recent Advances and Future Perspectives. And here I'd like to touch upon 4 closely related topics. First, I will introduce Artina, our deep learning approach for automated protein NMR data analysis. Then I will move to Artina extensions, which makes our method more versatile and data efficient. Here I have in mind mostly AlphaFold integration and time-optimized assignments. Then I will talk about NMRtist, our online platform that hosts Artina for the entire NMR community. And finally, in the last part, from my personal perspective, I will try to extrapolate current trends and try to predict what may bring some impact to NMR field in the near future. And here my personal favorite is shifting from human-centric to AI-driven methods in NMR spectroscopy. And the whole story in this presentation is based on the research carried out in our group. And the core part are these 2 research articles published in 2022 and 2023. NMR spectroscopy plays an important role in protein structure studies. So far, method contributed with over 10,000 models to protein data bank. Rich information content of NMR measurements makes it possible to explain protein structure, dynamics, and interactions mechanistically at the atomic level. Unfortunately, NMR spectroscopy suffers from certain limitations that renders the full potential of the technique unexploited. Currently, it takes weeks or months of manual work to transform set of multidimensional NMR spectra, here I have in mind 2D, 3D, and 4D experiments, into protein structure model. And this process involves peak picking, where the entire volume of the spectrum is analyzed to identify coordinates of recorded signals, then chemical sheet assignment, where identified signals are mapped to atoms that we know from the protein sequence, and then finally, structure calculation. Quite recently, at ETH Zurich, we proposed the first method that fully automates this process. Our deep learning approach, Artina, takes as input set of spectra, and then outputs peak positions, chemical sheet assignment, and structure calculation in fully automated manner. The process takes about few hours of compute time and can be executed even by non-experts. This diagram presents the interplay between main components of our Artina workflow. It starts with set of NMR spectra, 2D, 3D, and 4D experiments, as well as protein sequence. Then, in the first step, we perform visual spectrum analysis using deep residual neural networks to get coordinates of recorded signals with some uncertainty estimation. In the next step, we use these coordinates as input for FLIA algorithm for the chemical sheet assignment to get signal to atom mappings. In the subsequent step, we bring to the analysis information about thousands of structures solved in the past by NMR, and it has form of graph neural networks, which allows to reassess all signal to atom mappings and reinterpret initially observed signal positions. We call it chemical shift refinement cycle. In structure refinement cycle, we use current state of the chemical shift assignment to calculate 10 intermediate structure proposals, which are then validated by gradient boosted trees, and the best model out of 10 is used again as a context to reassess initially observed signals. In Artina workflow, we execute iteratively chemical sheet refinement and structure refinement cycle 3 times until the final structure is generated. In order to train all machine learning models in presented workflow, we had to collect substantial amount of training data. Unfortunately, it was a major effort because this type of data is typically not deposited in public repositories like PDB or BMRB. Therefore, we decided to exploit 4 data acquisition channels. First, we built a website where groups around the world could upload their published spectra and contribute to the training dataset. We also implemented a special software, a crawler, which systematically scanned FTP server of BMRB database. We also explored our collaboration network and contributed with our internal resources. In total, we managed to collect 1,329 spectra, which allows 100 protein structures to be reproduced out of the original measurements. This figure presents the summary of the data we managed to collect. In the middle part, you can find the PDB codes of all the structures. In the upper part, the bar plot presents how many spectra we collected for each structure, and it varies from about 6 to 20 spectra per protein. And lower part presents qualitatively which spectra are available for each protein in our benchmark. For each protein, we have carbon and nitrogen resolved nosy experiments because it's about structure calculation, as well as some arbitrary subset of other experiment types. This entire benchmark is suitable for method development in NMR, for testing software, but also for teaching purposes. And everything is now freely available at nmrdb.ethz.ch. Being equipped with such large benchmark dataset of experimental data, we started with pre-processing in order to prepare it for deep learning model training. And for that purpose, we cropped 600,000 such smaller fragments out of 1.3 thousand NMR spectra. And each fragment has been annotated to indicate whether the signal located in the central part of the fragment is a true peak or an artifact. So it is typical labeling for binary classification problems. In addition, we developed a small NMR spectra fragment generator, which generates such three-dimensional small fragments of size 64 by 32 by 5. So each row in this figure presents one three-dimensional fragment generated by our generator. The disadvantage of the generator is, of course, that the data may be slightly different compared to what we can actually measure. But the advantage is that we can generate as much data as we want. We can control difficulty of generated training examples, and we have unambiguous annotations of the signals. Based on this data set, we trained two instances of the deep residual neural network. The first one is, the upper one is responsible for the peak detection. It takes as input quite large fragment of NMR spectrum and outputs a binary variable, which indicates whether the signal is present in the central part or not. The lower instance takes as input smaller but three-dimensional fragment of the spectrum, which was previously annotated by the first model as a true signal, and then it performs the convolution up to three-dimensional components. So in order to train this neural network, we have to make sure that it satisfies certain properties, such as permutational invariance of the output of the model, and we achieve it by training the neural network with Humphrey loss. Once we combine these two architectures, we have a signal detector in some complex NMR spectra. So this movie, for example, presents subsequent proton-proton planes of carbon-13 nose experiment. And the markers indicate signals that are recognized by our deep learning model, because obviously signals may also lie in between two planes or are visible in several subsequent planes. We have these several types of markers, but what is important here is just to give some qualitative impression how the spectra of some larger proteins look like, and what is the data that is analyzed with our models. So once we have this signal detector, we use all the signals as input for the FLIA algorithm for the chemical shift assignment. And FLIA formulates this problem as combinatorial optimization. It is also worth mentioning that it's NP-hard problem. And in FLIA formulation, what we have here are observed peaks. So this is what our deep learning model found in the spectra. Because peaks are observed, we know their positions, but we don't know assignments, so we don't know to which atom these individual signals are mapped. On the other hand, we have expected peaks where assignment is known because you can back calculate them from a sequence, but position is known only approximately, because from some statistics like BMRP depositions, we know in which regions of the spectrum we expect to observe certain atoms, but we don't know precise location. So the FLIA assignment is about mapping these expected peaks to the observed ones. And FLIA uses genetic algorithms to evaluate thousands or even millions of such possible assignments. Each is evaluated using a special score to discriminate which one is better than the other. And the score consists of 4 terms. One is about completeness, because we want to obviously assign as many atoms as possible. And second one is about alignments, because we observe certain atoms in several spectra, and also within one spectrum, the same atom can be also observed several times. So we want to have this consistency. Then we have normality of assigned shifts. So how well assignment matches some statistics from BMRB database. And the final one is about degeneracy. We wouldn't like to have situation where, for example, many atoms are assigned to single peak. It would be also only theoretically valid solution, but in practice, it is not what is the correct solution. So deep learning appears in Artina flow workflow in many places and in different forms. So I here mention about deep residual neural networks, but you have also graph neural networks and gradient boosted trees. So discussing all these models is beyond the scope of this presentation. However, if you're interested, you can read more in the manuscript that we published about it. So now I would like to move to the evaluation of our workflow. So to evaluate our method, we carried out 5-fold cross-validation experiment where we use all 1.3 thousand NMR spectra to reproduce automatically protein assignments and structures out of experimental data. And then we compared the result of automated chemical shift assignment with the positions of in BMRB database and the result of structure calculation with PDB depositions. These 3 plots, they present the evaluation of the automated chemical shift assignment. So in the inner part of the circle, you can find the PDB codes of proteins. They are sorted clockwise by size. And then each bar presents the accuracy of the automated chemical shift assignment as compared with BMRB. So for example, for the backbone, our method achieves accuracy of 97.2%. This is the median value. And what can be also observed that the accuracy is quite stable across all protein sizes, which is in case of our benchmark between 4 and 20 kilodaltons. In case of the sidechain assignment, the accuracy is slightly lower, about 88%, and it is mostly due to challenges associated with assignment of aromatic residues. And finally, for the all shifts together, our accuracy is approximately 91%. If we look now at the structure calculation, the plots have the same structure regarding the RMSD, this backbone RMSD calculated between output of automated structure calculation and PDB. The median value across 100 proteins is 1.44 angstrom. And what can be also observed that among 100 proteins, there are only 3 where this RMSD is above 3 angstrom. Regarding the distance restraints, our model extracts about 20 such restraints per residue. So the same data is here presented qualitatively in the form of protein visualizations. So the structure calculated by Artina is color-coded in blue, and it is overlaid with corresponding PDB deposition, here color-coded in orange. In the upper part of the video, you can find the PDB code of the protein, RMSD, between automated and deposited structure, as well as backbone and sidechain chemical shift assignment accuracy. So part of the protein that has well-defined fold is presented with stronger colors, and the part which is flexible is presented with semi-transparent way. And this part that has a well-defined fold has been calculated using the SciRange algorithm. So in addition, all the 100 structures presented in this video are sorted by RMSD. So in the later part of the video, you will find the structures that are predicted with the least accurate way. So here I can stop for a few seconds such that you can also look at all these structures. Perfect. And this is the last one, the least accurate out of 100 structures. So obviously what is interesting is to look qualitatively, what are the errors that our automated approach makes in structure determination. And it turns that if we look at the 3 structures calculated with the least accuracy, one can find out that the problem is mostly associated with wrong placement of the first or last secondary structure element, such as here, for example, the alpha helix, the last alpha helix is pointing at the different angle, whereas the rest of the protein fold is typically predicted or solved with much higher accuracy. To further challenge our method, we also collected some spectra recorded with only 20% carbon-13 labeling. And this spectra feature a higher noise level as presented here in this figure. And we then use this 20% carbon labeled spectra as input for chemical sheet assignment and structure calculation. And this test in this case of this protein was also successful. The structure has been solved with about 1 or 2 angstrom RMSD. However, this protein wasn't that large, which also makes this problem a bit easier. So in all this analysis, we always compare the output of our method with some ground truth that was determined manually in the past. But if one uses this method to analyze some new data, we obviously don't know what is the correct answer. That is why uncertainty estimation plays an important role. In case of the chemical sheet assignment, our method generates such a diagram where each residue in the protein sequence corresponds to the column, and each position within residue corresponds to row. And dark blue rectangle corresponds to atoms that have been assigned by Artina with high confidence, and light blue some weak assignments that are rather uncertain. We also figured out that by looking at the proportions between strong and weak assignments, we can, to some extent, or at least quite approximately, predict what is the chemical sheet assignment accuracy, even if we don't know the manual assignments. Following some similar principles, we also established uncertainty estimation for structures called PRMSD. And as you can observe in the figure, our PRMSD is correlated with the real RMSD for the structures where we know the ground truth, and it has rather tendency to overestimate RMSD, saying that the structure is slightly worse than it is in reality, just to be on the safe side when it comes to interpreting the results interpretation. So in the second part, I would like to move to Artina extensions. So after we released our method in 2022, we worked to improve its data efficiency through integration with AlphaFold, as well as to expand versatility through making it possible to use it with some custom systems like protein ligand complexes, peptides, some non-canonical residues, custom ligands and metal ions, as well as we expanded to the solid state NMR by increasing number of NMR experiments supported by our platform to 73 experiments. And probably the most impactful or critical part was to integrate our method with AlphaFold. So to do this, we use the same protein spectra dataset that we collected for Artina development that consists of 1.3 thousand spectra that allows to reproduce 100 proteins. And then we use the spectra to form 29 spectra subsets. And each subset had a unique combination of experiment types. Subset number 1 was the most generous one, which contains all possible spectra, whereas subset 29 was the most restricted one which contains only nitrogen HSQC and nitrogen nosy. So it could correspond, for example, to a case where we have only nitrogen labeling of our sample. And all the other subsets were somewhere in between these two corner cases. Then for each subset, we executed de novo chemical shift assignment with Artina, but then assignment with known structure that was provided by AlphaFold, or with some other additional in silico predictions. And these diagrams present the output, the result of over 5,000 automated chemical sheet assignments made with this dataset. So the structure is the following. Each node corresponds to one spectra subset presented in the table, and the upper node is the most restricted dataset. So in that case, it is subset 21, which corresponds to two nosy experiments at nitrogen HSQC. And then each edge corresponds to introduction of one experiment type. So here, for example, we introduce carbon HSQC and then CBCA, CONH. And then as we go down in this graph, we have larger and larger data sets. So for each node, we also report de novo chemical sheet assignment accuracy, here color-coded in black. Then assignment made by Artina with additional input of AlphaFold structure, and then with additional input of AlphaFold and UCB chemical shift predicted out of AlphaFold structure. So what can observe here is that as we go along this graph, at some point we reach a point where we still use some smaller subset of original data, but when AlphaFold and or UCB shift are used as input, the accuracy of the assignment is already higher than with the full data set, but without any in silico input. So this way we figure out that by using the subset 22, we can record just 5 three-dimensional spectra instead of more than 10, and still get slightly better assignment than with the full data set. But of course, there is always question how in silico predictions they impact our results, and when they are beneficial and when they can harm the analysis. So first we tested whether such in silico break our uncertainty estimation, and the answer is that they do not, such that when we introduce AlphaFold and UCB shift, all the correlation still holds. Second question is looking just empirically at this 1.3 thousand spectra and 100 proteins, how frequently it is beneficial actually to use AlphaFold or AlphaFold and UCB shift. And the answer is that was almost always beneficial. And the third question we ask is, what is the tolerance for the in silico predictions? So assuming that our structure predicted by AlphaFold may be wrong, So how much it can deviate from the true fault such that it still helps with the assignment. And the answer is that if we use structure only, if it is within 3 angstrom RMSD from the true structure, it still helps to assign the protein. But if we use structure and then UCB shift prediction based on structure, then we have some error accumulation. And in that case, the 2 angstrom RMSD is the limit. However, in case of our benchmark dataset, AlphaFold was much better than these decoys. So regarding, for instance, the solid state extension, we currently support 73 experiment types that are listed here in the slide, but we offer different degree of support for all of them. So experiments marked by in green are the ones that are well represented in our training data. Therefore, we expect the best performance with them. The blue ones are supported and somehow underrepresented in training data, so we can observe some slight performance gap. And then finally, the gray ones are only partially supported. So one can, of course, run the full analysis, but the analysis will be made using deep learning models trained on different type of spectra. So in part 3, I'd like to talk about NMRtist, our online platform that hosts Actina for the NMR community. And this is the website that we built. Everybody can register account here and receive, I think it's at the moment 30 gigabyte storage where one can upload data, and then one can use this data to run some predictions with our deep learning models effortlessly. So our system got some traction in the NMR community. At the moment, we have over 1.2 thousand active accounts, and this map presents all public research institutions that have at least one NMRtist account active. So they cluster mostly in Europe, in North America, and in East Asia. But apart of numbers, what is important here is that we managed to establish a network which allows us to test new machine learning solutions for NMR rapidly and at scale. So these bar plots, they present the cumulative use of our platform over time. So the first one presents completed automated structural calculations. At the moment, we reached above about 4.5 thousand such completed jobs. In terms of chemical sheet assignments, we have over 11,000 completed. And important part is uploaded spectra. At the moment, our platform received about 30,000 spectra. Mostly these are 3-dimensional experiments. So in the past, it was major effort for us to collect this 1.3 thousand spectra of 100 proteins. And so we had to execute a project for about half a year to collect it. But now, by hosting this platform, we collected about 30,000, and they correspond likely to the decades of measurement time with advanced scientific instruments. But what is also quite exciting is that for the very first time, we are in position where we can execute terabyte scale deep learning project for NMR with experimental data. So this short video presents presents our platform. So it is just about 4 minutes. So let me maybe run it and comment. So all what you need to have in order to work with our platform is just a set of files with spectra and the protein sequence. And once you have account, at NMRtist, all you need to do is to create a project. Project is the way to define your system. So each system should have separate project. And to define system, the simplest way would be to just provide a sequence. But for non-canonical residues and more advanced systems, one would need, of course, to make it differently. But once project is there, all one needs to do is to upload data to the virtual storage associated with account. It can be done very simply, just drag files from your local file system and drop them in the web browser. All data is being uploaded and converted on the fly. A part of the spectra, you can also upload peak lists, shift lists, distance restraints, and some other files. Once data is there, one needs to provide metadata such that specify experiment type for each spectrum that is uploaded to the platform, provide the dimensions of the spectrum, determine whether there was some unfolding, some aliasing applied, and one can also provide additional input through a system of tags. For example, that spectrum contains only aliphatic peaks. Then one can also verify whether data landed successfully on our servers by looking at the spectra visualization generated by the platform and looking at the metadata extracted during the upload. Most of the time, our system can automatically extract this metadata if one follows certain standards. If not, one needs to set them manually. And once metadata is provided, in order to use our deep learning models, one just needs to select one of the applications, like the structure determination, and all it takes is to specify files that need to be used for structure calculation. And it in principle applies to all use cases, or all scenarios. NMRtist can automatically adjust the approach based on the input that is provided. After a while, your results are available, and what NMRtist outputs is comparison of uploaded spectra with other spectra of the same type, then peak list with the quality metrics, then detection of relative shifts between pairs of spectra referencing, visualizations of the peak picking on 2D spectra projections, then we have visualization of the chemical shift assignment together with uncertainty estimation, comparison of uploaded spectra with other spectra of the same type in context of percentage of assigned signals, and then assigned peak list with their quality metrics. Then it also reports visualizations of the chemical shift assignment back calculated onto the spectrum. And finally, we also have the protein structure. NMRtist gives always two structure proposals together with some statistics and the source data. So if you would like to try the platform, we also provide some example data here in the Getting Started tutorial part. But of course, you can also download any spectrum from this 1.3 thousand data set that is also available online and test with our system. So there are several use cases that our platform covers. So the video presented only the basic one, but in principle, for the chemical sheet assignment, we cover the de novo assignment, where one needs to provide NMR spectrum and the protein sequence, and obviously one gets the chemical sheet assignment with all intermediate steps. But we also support chemical shift transfer. It is the case when the chemical shift of similar system or the same system under another experimental conditions are known, and we want to transfer these chemical shifts to the newly measured system. In that case, one needs to upload some chemical shift statistics and provide it as input for our application. There is also structure-based assignment, where you have set of spectra and the protein sequence. And we, for example, know the structure because it is available from X-ray or cryo-EM, or we trust our AlphaFold prediction enough to use it as input. Then we have also conditional assignments, where we have some subset of atoms that were assigned manually. We, for example, have backbone, and we want the system to complete the assignment for us. In case of structure calculation, it follows some similar principles. So we have de novo structure calculation, chemical shift transfer with structure calculation, conditional assignment with structure calculation, and structure determination with additional restraints. So that would be about presentation of the platform. And finally, I would like to move to the last part of my talk, which is about charting the future and trying to predict what may be impactful in the upcoming years. So the direction one, which I find the most interesting one personally, is advancing beyond the automation of data analysis. So although automation of the structural calculation and data analysis is an interesting problem in itself, one can always ask the question, can we go beyond automation? So can we design a new way of studying proteins in NMR that are maybe very difficult for humans, but still fully compatible with deep learning? And at the same time, we could have some properties or we can eliminate some bottlenecks that exist with traditional workflow. So this is the traditional workflow that I discussed so far in my presentation, where we start with set of spectra, then we perform peak picking, chemical sheet assignment, and structure calculation. And this is what we are working on at the moment at ETH, where we try to record single free channel spectrum. It is made by stacking 3 two-dimensional experiments, 2D nosy, 2D toxy, and 2D cozy. So here we rely only on proton measurements, and then such free channel spectrum undergoes deep learning-based visual and semantic analysis. So here we need to have much larger model to perform analysis. And then this model not only detects signals in the spectrum, but also for each signal, it predicts from where the signal comes from. And having such dense annotations of signals, we can then use other algorithms to reconstruct a chemical sheet assignment and the protein structure. So why we think that this approach is interesting? First of all, we do not need a carbon and nitrogen isotope labeling to study our systems, which can simplify the sample preparation, also reduce the cost, and there are multiple benefits of this. Second argument is that because we measure only 3 two-dimensional experiments, we need about 1 day of measurements instead of 7 to 14 days with this traditional approach. Thirdly, it constitutes a justification for 1.2 gigahertz measurements because a compact data set requires a good spectral resolution. This is also a great justification for large state-of-the-art deep learning models. And the whole protocol is also versatile. It can be used for assignments, structure determination, dynamics interactions, because all relevant information is stored in this, especially 2D nosy experiment. And finally, deep learning prediction is not the black box, but it can be verified against this experimental data. Because although it will be very, very difficult for a human to solve the structure based on such limited input, when this input is available, because it's predicted by deep learning model, one can project this output onto the spectrum and one can manually verify whether what model predicted fits experimental data. The second direction is about terabyte scale deep learning with NMR experimental data. And this refers to some usage statistics that I presented before in my presentation. So we hope that at some point we'll be able to implement self-improving feedback loop in Artina, where the performance of our online platform scales proportionally to number of uploaded spectra, but also hopefully number of uploaded spectra will scale proportionally to the performance of our method. One can think about multimodal learning in NMR spectroscopy, where various type of data is integrated to build a protein structure model. We can also think about expanding current data analysis to incorporate additional dimensions, such as, for instance, protein dynamics. And we can also train deep learning models that truly captures diversity of NMR data, because to establish the first version, we use 100 proteins and 1.3 thousand spectra from still several groups in the world, but it's not the same as collecting data from more than 1,000 users and look at all possible ways they process data, they record samples at all possible systems they study, and then training deep learning model based on all this data. So another direction is expansion to solid state NMR, and this is the project that we execute in collaboration with Bruker. So here the main challenges are associated to adaptation of the first parts of the workflow, because in solid state NMR we have different experiment types, also different peak broadening that need to be accounted for. However, the remaining part of the workflow is already quite suitable for this. And then the final direction is about building some larger scale models for NMR spectroscopy. So in recent months, I read about 70 articles at the intersection between machine learning and NMR spectroscopy, and wrote some literature review on that topic. So what one can see is that looking at all these articles published over last years, the work mainly clusters around spectrum analysis. It was the core topic of this presentation, where deep learning is used for peak picking, chemical shift assignment, or structure determination. Second large area is structural property relationship prediction, where we have sub-problems like the chemical shift prediction, scalar couplings prediction, or protein dynamics. And the third one is about spectral reconstruction and quality enhancement, NUS reconstruction, virtual decoupling, and denoising. This is the figure from our paper and presents all the methods and problems that they touch upon, as well as machine learning approach selected. So the conclusion that one can draw from the study is that most of these methods are quite fragmented, that they address some specific aspect of NMR, but it would be interesting to build some larger solutions that, for example, in our case, we can do assignment and structure calculation, but how about also doing dynamics and maybe at the same time look automatically at the spectral reconstruction and quality enhancement, such that you can predict structure and dynamics using some smaller data set or lower quality data. So one can ask question why we think it is a good moment for NMR and machine learning. So first of all, it is because we now collected unprecedented amount of NMR spectra. And we are also in late state of development of physics-based NMR spectra simulator that allows training new models with potentially hundreds of thousands of realistic NMR spectra. And what you can see here in the figure is actually not the real measurement, but output of our physics-based simulator. We also now have a network which allows us to validate such deep learning solutions at scale. And also because deep learning is still quite underexplored in context of NMR, especially most influential architectures like transformer or diffusion models are rarely used with NMR data and not at scale. So as the very last part, I would like to just make a point that all these predictions is not something that lives only in our imagination. It is something that we are actively working for. And especially about this first part, moving from human-centric to AI-centric methods in NMR spectroscopy, we currently work on large-scale vision transformer for NMR. And our model architecture is inspired by article published by Google in 2020, and image is worth 16 by 16 words. So this is the architecture of the model. What is interesting about it is it analyzes the NMR data at, I think, different level. So the previous model that I presented in my talk, it takes some small fragments and tries to infer whether fragment contains a peak or not. But here, the new model, it takes as input entire NMR spectrum. It tries to reason about everything what has been recorded in the spectrum simultaneously, and then output not only the peak coordinate, but also its interpretation from which atom it comes from and what it represents. So this is example of 2D nosy generated for our generator and then picked by our vision transformer. So what you can see is that the quality of the peak picking is not bad at the moment, and also that a part of the peak position, it also outputs some uncertainty about positioning, which is actually very, very important when we work with such limited amount of data. So what is also interesting is that because the analysis is deeper, we can also query the model. So we can ask our vision transformer, for example, given this 2D nosy spectrum, to predict where are arginine signals. And then what model outputs is here indicated by black. The red is the ground truth. It is still not perfect, but one can see that first of all, it is correlated. And secondly, is that these predictions are non-trivial because it is not that we observe arginines in some region of the spectrum that one can say that using some simple rules, one can say where they are. It is about reasoning about the whole spectrum and finding some precise positions where arginines are located. One can ask also about the lysine or any other amino acid or any atom in general. So we have also some early success with solving structures out of these 2D experiments only. So these are relatively small structures, 1975 residues, and it is still quite early stage. So it will take some time before we introduce this technology to our nmartist.org platform, but it is something that we actively develop. So main takeaways from my talk is that we establish a new data set for liquid state protein NMR that allows 100 protein structures and assignments to be reproduced out of original 1.3 thousand spectra. We developed Artina, the first fully automated deep learning approach for protein NMR that covers peak picking, protein assignment, and structural determination. We also implemented and launched NMRtist, an online platform that makes all these models publicly available. And the future developments will likely focus on 4 strategic directions. It is shifting from human-centric to AI-driven NMR methods, developing terabyte-scale deep learning solutions for NMR, adapting Artina to solid-state NMR, and building some larger, maybe even foundational model for NMR spectroscopy. If you are interested in this research topic, the presentation covers basically 4 articles that were published between 2022 and 2025. And at this point, I would like to acknowledge Luca Wenchel, who is a PhD student working on physics-based spectral simulation, my supervisors, Professor Ron Trick and Peter Gintert, as well as the whole RIGS group and NMRtist users for their continuous feedback on our deep learning solutions. We also received generous support from various sources, including European Commissions, Swiss National Science Foundation, ETH, and Bruker. And that's all what I prepared for today. Thank you for your attention.
Thank you very much for fascinating talk. So we're open for the discussion. If you want to ask a question, turn on your microphone. Do we have any questions?
I have a question, if I may. Hello, Piotr. Thanks for an interesting talk. Maybe I missed something, but do you make any use of PDB data that doesn't have NMR assignments, like PDB structures determined from X-ray or something? I mean, for training.
So we use it in NMRtist workflow. So let me find the slide. So we have this structure-based assignments, for example.
Yes.
Where you can provide the spectra with the sequence as input. And then PDB structure could be X-ray, could be NMR under different conditions, could be AlphaFold. And then it typically helps a lot with the protein assignment. One can go even one step further, that given this X-ray or AlphaFold, one can also predict chemical shifts with tools like UCB shift or shift X. And then one can feed both structure and this shift prediction, and both are then used to find assignment. So it doesn't work well for the structure calculation because there is a tendency that our method outputs something that is correlated with the input AlphaFold structure. So if there is a mistake, then it doesn't make sense. But for the assignment, it works.
Okay. Because, I checked very quickly the outlier that you showed, what was it, 2M47 structure that you showed to be deviating. And there is a paper describing this structure. And what they mentioned there is that the structure is very similar to several other proteins in PDB except for the position of first alpha helix. So I wonder if what you show here isn't a problem of overfitting, that you use that, because these structures from PDB that I mentioned and that they mentioned, they don't have NMR data. So I was interested whether you could have them in your training data set and simply overfit or something. So how big is the problem of overfitting according to your experience?
So in the case that you mentioned, it is irrelevant because we don't use structures for training. So what we do is we use deep learning to analyze spectra. And at the moment, not even the whole spectrum, a fragment of a spectrum is used as input. So so I think this maybe not very critical that some specifics about individual structures.
Okay, thank you.
May I ask a question?
Yeah, of course.
Hello, Piotr.
Hello.
I have a question, perhaps somehow related to this slide. You are surely aware of the work of Fleming Hansen. One of them was about virtual decoupling, right? So
Yes.
very often we have spectra where homonuclear couplings are difficult to remove experimentally. And does Athena somehow like implicitly address this problem? Because in your training data set, surely the data has these homonuclear couplings. Can we say that this machine learning approach already recognizes the pattern, and we don't have to say anything more? That it knows that the couplings are there, and therefore it extracts higher resolution. Can we say that?
So I think that in vast majority of cases in protein NMR, we don't observe couplings. It's simply related to the magnetic field strength and the sample size.
No, wait, agent CA has couplings.
Yes, but still, if we observe them, then it is better to first use this virtual decoupling and then use it as input for Athena.
Okay, so you would still advise to do it as a first step before running
Yes.
Athena. Okay.
I see Justyna is raising hand.
Hello, Piotr. Let me see if I can switch on my camera. Or maybe. Is it coming? Hopefully. If not, then
Okay, we can see you and hear you.
Okay, sweet. Hey, Piotr, it's a really, really great work. And I followed from your first paper, of course. So I have a question for you. Let's say that you have 80 kilodalton protein and you really can only have metal labels, ALVs. You can easily guess that I'm not getting into this really structural assignment, but what I'm getting into chemical shift predictions. So do you think there is any use of leveraging your data sets, all the cleaned and parsed data sets you generated, to improve the chemical shift predictions of the metal groups? Is it possible to do that, and how well it will perform?
So
and let's say, assuming I use AlphaFold or X-ray, because currently it really doesn't work well. Yeah, let's face it. So can one leverage the tools you generated to get there better?
So indirectly, maybe. So in order to build a predictor for the metal chemical shifts, one would need to have quite large data set, and probably at the moment the largest what one can get is through correlating BMRB and PDB. And then maybe one can get a few thousand proteins, and each protein has also quite many metal groups. So we are in the range of maybe thousands, tens of thousands. So it is something, but not sure if there's a good foundation for some really robust model. And so it would fall mostly to this structural relationship prediction that I mentioned in one slide. So what we could possibly have to have some advantage in building such metal chemical shift predictor is that we already have quite a lot of data, and we have all these automated assignments. And we also know whether metals are assigned with high or low confidence. So probably by analyzing all these uploads, we could expand this data set and then propose something in this direction. But platform itself is mostly for analyzing experimental data. And we have also in our backlog metal assignment. I don't know if you work with Metal Flyer, for example, but we also plan to incorporate it such that one can do assignments based on the AlphaFold or other structure plus some spectra uploaded, and then get some experimental metal assignments.
Yeah, but here you probably also have a cut of around 30, 40 kilodalton protein, yeah? So you will not get to the regime of above 50, I guess. Is that a correct statement?
For a moment, yes.
Oh.
For a moment, yes. But we also receive uploads from outside the original target group. So, for example, we have like 500 peptides also being uploaded, although the system was designed for proteins and 3D experiments. We have this unlabeled samples and peptides being uploaded. I think we have also quite some uploads of larger systems. I think there is some plots maybe that I presented. It will be in the last part. So this is more or less the distribution of the system sizes. So I think the largest one are like 2000 residues. That would probably also fit into the regime that you have in mind. There are not many because we don't provide specific tools for this, but there is a hope that once we have metal assignment models or applications in the system, we'll also get more larger systems. Another question is that how local is the problem? Because what the distance at which we have these interactions is typically probably about 6 angstrom or so. So if we do metal prediction, then probably the input data is this metal group plus some sphere about 6 angstrom radius around. So maybe one can also extract these spheres from smaller systems, and this will be equally valuable input for training as the larger ones.
Okay, I think Gabriela is also trying to ask the question.
Yes, thank you very much for your presentation, and I think that you kind of answered my first question, but I still gonna ask it because I just want to know if the prediction, that the structure calculation of the peptides is good in the NMR test. I mean, if it's trustable. And the other of my question is if you can use also like peptides or proteins with modified amino acids. Is it possible in the NMR test?
So regarding the first question, it is possible to upload peptides, but there may be some performance gap because we trained our models using the triple resonance experiments, and here there are 2Ds associated with peptides. So some people successfully upload and they have analysis at a decent level, but it is something that we try to address at the moment. And especially it falls into direction of this proton-proton measurements and the new vision transformer model. So if everything goes well, I cannot promise, of course, but this year there may be also a solution for peptides and for 2D experiments that would help a lot. And regarding non-canonical residues, it is possible. So in principle, one can define any biomolecular system in our platform. Of course, just to stress again, we develop it for proteins, but one can also try to use it with something else.
Oh.
And for non-canonical residues, one needs to prepare a small text file, which is called Cyana library, which defines configuration of atoms in such non-canonical residue and new three-letter code associated with this definition. And then one can use this three-letter code while defining the system and the sequence in the platform.
Okay, so I understand it can be found somewhere on the website how to prepare your own amino acid, or
So in general, yes.
Okay.
It will be more in the Cyana documentation because Cyana is one of the major building blocks which is behind our website. And if you have some problems with finding this information, then of course you can write an email and then I will try to help. Or if you have some like very specific non-canonical amino acid that you would like to prepare, then you can also contact us.
Okay, perfect. Thank you very much.
Do we have any other questions? Let's give it a moment. Okay. Yeah. Okay, I think we ran out of the people asking questions. So let's thanks once more Piotr for great talk. I think we broke the record of the longest seminar in our series, which is also quite interesting and good. And let's just announce the next, in 2 weeks, we'll have two talks. First, is, as usual, a student talk by Farwa Khalid, my very own PhD student. And the second would be from Mateusz Słowiński from Faculty of Chemistry, University of Warsaw. And he will talk about his whole PhD because, as far as I understand, he is just going to defend. And of course, I asking everyone who wants to give a talk to email me. We have still 3 spots available for full talk in the next semester and quite a lot of PhD student talks also available. So if you want to give a talk, let me know. I'm always looking for another speaker. So thank you very much for both speakers and see you in 2 weeks.
Thank you. Bye.
Thank you.
Thank
Bye.
you.
Thank you. Bye.